Hello.
Hello.
Hi, you can hear me, see the desktop, right?
Yeah, I can see it.
Okay. All right. Let me see. Okay, I'm just getting up Windows so I can see what's going on. Okay. Okay. We want to see if we can finish these two sections on the abstraction and the mechanism. Okay, there's two topics that we haven't talked about yet, and they're each kind of in one of these sections. Okay, the two topics that we haven't talked about are process states and system calls. Okay, so there's a zip file here about process states, and there's another one for about system calls, but I didn't put it up there on the website yet. We'll see if we get to it today. I've got a shortcut to it here. Let's see, where did it go? Okay, so I've got it downloaded. I've got it on my desktop, but I haven't put it up on the server yet. Okay, so we have to talk about process states and system calls. Now, process states are on, see there, this section 4.4 in the chapter on on abstraction, okay? And the system calls start, where is it? Oh, did I open? No, that's the same one. I'm sorry. In the one on mechanism, he starts talking about system calls here. Okay, so there's a lot in here about system calls. Okay, so what we want to do is we're going to go back. We're going to try to explain things by pictures. Okay, so and what we're talking about is a lot to do with CPU architecture, especially the stuff about system calls. System calls really force you. They have to do with the user mode, kernel mode thing. Okay, and their system calls are what are another word for them is software interrupts. They're a form of interrupt you control with software rather than hardware. So system calls is actually a synonym for software interrupt. So it's very much a hardware question. It's really where software and hardware merge. Okay, this system call is where the CPU architecture merges with the idea of writing code, right? And that's closely related to this idea of process states. Okay, so let me bring up the picture. Um, let's see which picture. Okay, so I'm going to download this picture and use it to start with. Okay. And I'll open it in Paint in case I want to make any changes to it. Okay, this is our basic kind of like go-to picture of how we want to think about this stuff. Okay. Okay, we're real simple basic thing. We're running two processes in memory. Okay, so we've got a process 0 and a process 1 from program 1 and program 2. Okay. Now we've only got one CPU. So our model is of a single CPU. Can I make the mouse pointer bigger? There. Okay, there's a bigger, slightly bigger mouse pointer. What'll give me the biggest mouse pointer? No. Okay, so we've got a single CPU, but two processes. So we know what happens is that the CPU will be running one of the processes until this timer interrupt happens. When the timer interrupt happens, that causes the hardware, that's a hardware interrupt. Remember, it forces a specific address into the program counter, which directs the CPU into the operating system kernel. and it also switches the computer from the CPU from user mode to kernel mode. So now it's essentially called into the operating system, and it goes specifically to the device driver of the timer. Okay, so that puts you in the device driver of the timer. That belongs to the operating system. The operating system then chooses to make a context switch between the running process and another process. To make the context switch, the operating system takes all of the CPU register and puts them in the process control block of this process. So that's saving the state of the CPU so that you can go back to it. So all of the CPU state is put in the process control block. Then the operating system goes and looks at this other process control block. It takes all of the state of that process control block, puts it in the CPU. Now, part of the process control block is a program counter. So that essentially sets the program counter inside this, and the CPU picks up where it left off in this process. This process doesn't even know it ever lost the CPU. From the point of view of this process, the CPU executed one instruction. The process doesn't know that the CPU was taken away from it, and this process just sees the CPU execute the next instruction. This process has no way of knowing that in between two instructions, the CPU is actually running some other process. Okay, that's the virtual CPU. So what we're creating here is this impression that this process has a virtual CPU that runs in user mode. Quick review. Why do we need kernel mode and user mode? Why do we have the two?
So that the process doesn't take over the CPU.
Okay, I couldn't hear you, but I think you had the right idea. So the process what?
Doesn't take over the CPU.
Yeah, essentially that's it. You can't let one process say, hey, I don't want to share anything. What if it just took over the CPU? What if it just erased the operating system from memory by writing zeros there? What if it erased this guy from memory, writing zeros there? This process could run it's running its own code. What if it decides to be malicious? Well, the kernel mode, user mode distinction prevents that. When this guy's running in user mode, he cannot see out of that red box. He can't see this memory. He can't see that memory. If he tries to look at that memory, he's shut down. He crashed. He can't change that interrupt. If he tries to change that interrupt, the CPU would detect that in user mode, he tried to change an interrupt, and the CPU hardware will crash the program. Okay, so when the process is running in user mode, the CPU, this virtual CPU, is limited in what it can do. And it's limited so that it can't maliciously attack either the operating system or another process. Okay. The only way to get back into kernel mode is by one of these interrupts. So these interrupts put you, but then they take you into, see, these interrupts do two things simultaneously. They switch you from user mode to kernel mode, but they force the program counter into the operating system code. So there's no way you can be up here in kernel mode. There's nothing that would let this program over here suddenly switch into kernel mode. If he could switch into kernel mode, he could take over the CPU. When because of this was a brilliant design. This design goes all the way back to the 60s, but the idea was that you would have special code up here called the operating system, and the CPU hardware would be simultaneously switched from user mode to kernel mode and directed into the operating system code simultaneously. So this is the trusted code that everything hinges on. You have to suppose that this thing's not malicious. If this code is malicious, anything can happen. So if somebody can plant malicious code in the operating system, which is what all hackers wish they could do, is they try to plant malicious code into the kernel. If there is malicious code in the kernel, then you have a real problem, because the kernel is in kernel mode. It runs in the kernel mode state, so it has total control over things. Okay, so it can steal passwords, it can do anything it wants. Okay, so the idea is that the operating system code has to be trusted code. That's the weak point of this. Okay, all right. Now, when this process is running on the CPU, this one's not. That gives us a sense that these processes can be in more than one state. For example, This process could be in the state of running, while this process is in the state of being ready to run. Okay, now that's this picture, that's this idea over here in the textbook. There are three, we'll see that there are three process states. We just talked about two of them, running and ready. Okay, when a process is running, only one process can be running on a CPU at a time. So this is this state, only one process can be in this state, the process that is currently running on the CPU. And then ready are all the processes that are ready to be run on the CPU. These are the other processes that when this timer interrupt occurs, the operating system gets to choose what other process to context switch into. The processes that are available to context switch into are the ready processes. This is a queue. We think of this as a waiting list, a queue. This is one process. This is a queue of processes. Okay, notice that the words here, when you're picked to run on the CPU, you are scheduled. And the next chapter is on the scheduling algorithms. When you are bumped off the CPU into the ready queue, because you have to wait till the next time, you're descheduled. Okay, so you're descheduled. You're put back in here. Now you're one of the ones waiting your turn for the CPU. Right now, these two just alternate. One's in the run, one's running and one's ready, and then the context switch would make the other one running and the other one ready. But in general, like on my computer, I have, well, I showed you, I have like probably 100 processes running, which means, well, I have 12 cores, I have say 100 processes. So I could have 12 processes running, one on each core. And then all the other processes would be mostly when they're ready. Though we're going to talk a minute here. There's this third state we have to talk about. That's where the other idea, the system call, comes in. So we'll bring that up in a minute. Okay, so a small number of, if you have one CPU, only one process can be running. Okay, one process running per CPU at most. Okay, and then all the other processes that are waiting their turn are in the ready queue. And the scheduling is done by the operating system. It's the operating system when the timer happens, when the timer interrupt happens, and the program counter's trapped into the kernel. That's when the kernel runs its scheduler to decide who do I context switch to. Okay. Notice there's a lot of words we're using, and I want you to learn these words like interrupt, user mode, kernel mode. We say that the program, remember I said when the interrupt happens, a particular address is forced into the program counter. That's often referred to as trapping. The CPU is trapped into the kernel. Okay. Yeah, and in some older computers, the interrupts were called traps. Okay. There's a lot of these words floating around that have been used synonymously. Another word is interrupt vector. The specific address that gets put into the program counter when this interrupt happens is called the interrupt vector. It sends this guy over here. So it could be the interrupt trap, the trap vector. Unfortunately, there's a lot of these words. Okay. So the interrupt forces a specific address, and that traps the CPU into the kernel, and specifically into the device driver of the timer. And then that thing starts doing the kernel's job of deciding who to schedule next, who should be scheduled next. All right. Now, let's add another layer to this problem. Okay. What if this program, let me add, like the disk drive has files on it. Right now, the disk drive has two files. Okay. There's the EXE files. The EXE files that these two processes were created from. Okay, now let me put another file on the hard drive, a data file. So suppose there's a data file down here. So a data file, okay? Right. Suppose this process wants some of that data loaded into his memory space. So this process wants that data to be copied here. Okay. So he wants the data to be copied here. The process is simply not allowed to go over to the hard drive, copy that data into its memory space. That's not allowed. If that were allowed, this process could go into that program file, modify it so that when that program runs, it does something malicious. Okay. If this process could reach into those files, if it could reach into the hard drive, it could reach into files and manipulate them. For fact, like the operating system actually sits on your hard drive. We saw it. If you go over here to the C drive, the Windows directory, and then the System32 directory, you're actually seeing all the files of the hard drive stored on the hard drive ready for boot time. And you can see there's thousands of them. There's 4,800 files in here. A lot of them are programs, but a lot of them are also the pieces of the chunks of the operating system. These are, there's just a mess of stuff in here. It's all very disorganized. It's kind of weird that Microsoft chooses to put 5,000 files in one directory. If this was a Linux machine, these files would be all pigeonholed into all kinds of different folders all in the hard drive saying what they do. So they would be, they would essentially be pigeonholed into subdirectories according to what they do. Now, Microsoft has a few subdirectories over here. There are subdirectories for various parts of the operating system, but then there's 4,000 other files just sitting there. Okay. Now, these are crucial pieces of the operating system. Some of these are very crucial pieces of the operating system. The code that manages this passwords. If any program could reach into the hard drive and write data anywhere it wanted to, you could change the program. You can modify the program that updates passwords and have it mail you all your passwords. So now notice that these files, like right now, if I say I want to delete that file, okay, see, it won't let me delete it. I have to type a password. I can delete it if I type in the system administrator password. I can't, but it won't let me do it. These are protected files. Okay. I can't, the Explorer by itself can't even delete them. See, remember, I'm running the Explorer right now. When I go over here and click on this file and hit the delete key, I'm telling the Explorer to delete that file. The Explorer asks the operating system to delete that file, and the operating system responds back, I need a password. Okay, so the operating system is responded. This is actually coming from the operating system. It's not coming from the Explorer. This is Explorer being told by the operating system, you need a password. Okay, so actually this pop-up may be I don't know if this pop-up is, I don't know. I think this pop-up is the operating system. I think when the Explorer asks the operating system to delete that, the operating system somehow puts this pop-up here. Okay, I don't think it's Explorer that's actually doing the pop-up. Okay, so these files are protected. All right, so then how can a process get data into its memory space so it can manipulate the data? How can it get this data copied in here? The program has to ask the operating system to do that for it. Okay. Programs are not allowed to access the hard drive. Only the operating system can access the hard drive. If a program wants to read data from the hard drive, the program asks the operating system to do it for it. That's called a system call. A system call is a special kind of function. It's a function where you ask the operating system to do something for you. It's calling a function in the operating system, okay? A system call, this is not 100% accurate, but it's a good enough way to think about it. Yeah. So a system call, you can think of it, it is a way to okay? It's a way to call, a way to call a function in the operating system. Okay, now, for example, if I call math.sign That's not a system call. That's a function call that's in the library. And that's just some code that I didn't write that just computes signs for me. Okay, that's not a system call. Okay. On the other hand, I can call in. I'll use Java notation. This is actually a system call, or I should say, this leads to a system call. Okay. Print line wants to put information on the console screen. That's doing some I/O operation. All I/O operations we'll see are done by the operating system. Every time you want to do, like another example of this would be if I do, well, I have in Java, I would do something like create a scanner and then do like int dot in dot next int. Okay, that's reading. Okay. Create a scanner object that's connected to the keyboard, or actually system in. Maybe it's the keyboard. Then read from it. Oh, okay, next int. Reading from the keyboard is going to be this leads to a system call. Okay, because you're asking for something from a hardware device. Okay. Now the more elaborate things is like when you want to read data from a file. So when you want to open a file and read data from a file, again, those are system calls. Okay. Whenever there's functions that aren't system calls. They're just like that. That just means you just call that function. The function is just a little bit of code written for you that makes things easier for you to do. So another one would be like that's not a system call. That's a function call. You're calling the to uppercase method on the cat string. Okay, so that's not a system call. Simple. If there's no I/O involved, the function call is not going to be a system call. Okay, if there's nothing involving I/O, but if there's anything involving I/O, like printing or reading from the keyboard, or more importantly, opening a file, those lead to system calls, because system calls, the operating system owns, oops, where's our picture? The operating system owns all the hardware devices. Remember, and we actually said in another time, remember, there is an interrupt from the hard drive into the, oops, there is an interrupt from the hard drive into the CPU. Okay, that's another interrupt. And it's the way that the hard drive and the operating system can communicate. They essentially kind of communicate through this interrupt. Okay, the CPU is connected to the disk drive. The CPU is connected to everything, but this process has no way of controlling that interrupt. This process has no way of actually communicating with the hard drive. The CPU must be in kernel mode to process that interrupt or to communicate with the hard drive. Turns out that the CPU and the hard drive are connected by more than just an interrupt. Okay, they're actually connected by a special I/O bus. Okay, so there's a special connection between the CPU and the hard drive and memory also. The The hard drive is connected to the CPU by a special bus, and it's connected to memory by a special bus. But no program has access to any of that stuff. All that stuff is part of kernel mode CPU. When the CPU is in real mode, the CPU actually doesn't even know the hard drive exists. Okay. When the CPU is in user mode, when the CPU is in user mode, the CPU doesn't, this virtual CPU does not in any way see this hard drive or the network interface card or the timer. Okay. So the virtual CPU doesn't know about these. Okay. Now, so what does a program do if it wants to read data from the hard drive into memory? Okay. So what it has to do is it has to go through a process of, first, it has to make a system call into the operating system to say, open that file. Then the operating system essentially opens the file and makes it ready to read data from it. Then it has to make another system call to the operating system to say, get some data from the file and load it into my buffer here. So this would be some array in memory that it wants this data copied into. So we would call this a buffer. Okay, an array that's used to hold data that you're going to read from a file is usually referred to as a buffer. Okay, so it becomes a two-step process. Some code in here has to ask the operating system to open that file. Then some code in here has to ask the operating system to copy data from the file into this buffer. Okay, that's done through system calls. Okay, what really happens is you call a function like printf. Your program calls a function like printf, like printline or nextint. What's buried in this code is the system call. The system call is actually, we say that this function is a wrapper for the system call. That's why I say this leads to a system call. Your program calls this function. This function actually makes the system call. Your program calls this function. This function actually makes the system call. Okay. Now, what does a system call actually do? A system call is a software interrupt. When this program makes a system call, it actually does two things. It forces a particular address into the program counter, which traps you into the kernel, and it switches you from user mode to kernel mode. Okay, so now a function call does one thing. A function call, a regular function call, like when you call to uppercase, you stick a particular address in the program counter. You jump to that function. Okay, so a function call does one thing. It puts a specific address in the program counter. That directs the program counter to the code that is that function. A system call does two things. It puts a specific address in the program counter and switches you to kernel mode. But there's a restriction. A function call can call a function anywhere in memory. See, when you call a function, the two uppercase can be anywhere in memory. I can write my own functions. I can put them anywhere in memory. I can call a function anywhere in memory, as long as it's my memory. I can't call functions in his memory. Okay, and I can't call functions in the kernel. I can call functions anywhere in my memory. System calls can't be called. You actually don't system call to a memory. You system call to a vector, and you system call to a specific. It's like there's a system, just like there's these specific interrupts here. There are a specific list of system calls, and each system call is associated to a specific address in the kernel. And then there's a system call instruction for each one of the specific kinds of system calls. Okay, it's not as arbitrary as a function call. A function call can call any address. You can start a function anywhere in memory. System calls don't start anywhere in memory. There's just like there's actually a table of them in the kernel. In the kernel is a table of system calls. This program counter can only jump into that table. So when a program executes a system call, it's actually choosing which entry in this table to jump to. So there'll be an entry in the table for reading from the keyboard. There'll be an entry in that table for printing to the console. There'll be an entry in that table for opening a file. There'll be an entry in that table for reading data from a file. So everything that this program would want to do that needs the operating system's help, the operating system has an entry in that table. Okay? And so then this program calls the system call. I can, here's like a weird thing to look at. Here's the system call table. Here's a documentation of the system call table for Windows. See, this is the Microsoft system call table. This table is actually sitting in the kernel, but somebody created a website documenting the table. Okay. In fact, that table is changed from operating system to operating system. So these are the system calls, and they shuffle the table from time to time. So like this column, like right now, we're over here in Windows 10. Yeah, there. And then Windows 10 has actually various versions of Windows 10. This system call table is buried deep in the operating system. So the idea is that you're not supposed to really know what's in it, and you're not supposed to really care what's in it. But somebody went to the work of documenting what's in it. But what's in it keeps changing with every version of Windows. Like this version of Windows, this was released in 2015. This is the current version here. The current version is released in April of 2020. And then this is the current, this is the one being released right now. This is the version of Windows 10 that's being rolled out. This is the one that was last rolled out. See, this one was released in 2019 in September. This is the system call table. This is one of the features that the operating system does for you. Access check by type, whatever that is. Notice it's got a little NT in front of it. NT that was the original name of the Windows operating system. The Windows operating system was called Windows NT. So these system calls are all named after the original version of Windows. So that's the NT system call that's access check by type. That's its entry in the system call table. Well, that's what its entry was in that version of Windows. Oh, it hasn't changed. Okay. And a lot of these aren't changing. Okay. A lot of these aren't changing. But every once in a while, something will change. Actually, sometimes they'll add a new entry. Like here's a system call that got added. See, it wasn't there, then all of a sudden it appears. That's something that got added to the operating system. Microsoft's they're deleting things and adding things to the operating system. So you can see when a system call is added to the operating system here. It didn't exist before. See, it didn't exist in these previous versions of the operating system either. Okay, so it was created there. I wonder if there's any that died out. They usually don't go away. Though sometimes they go away, but usually they don't go away because they're needed by old programs. Notice that there's somewhere around a couple hundred maybe of these system calls. This is from the point of view of a programmer, this is the library that the operating system gives to you to write your code with. Okay, this is the library of stuff that the operating system can do. If you want to know if Windows can do something, what you're asking is there a system call to do it? Oh, there's create file. That's a real important one. That's how you ask the operating system to create a new file on the hard drive. See, where's my picture? Okay. If I wanted a new file created on the hard drive for me, I would have to call that system call. Now, system calls are very hard to program with. So you don't call that system call. If you want to create a file in Windows, what you do is, I'm trying to find I got so many things open. Oh. See, there's a function called create file. That's a C function. What's the job of that function? To give you an easy interface into calling that create file system call. The create file function is the human readable, human usable call way to use that system call. So if my program wants to create a file, my program calls the Windows create file function. Now that function sits in my code. That's in user space. This function would be part of your program. It sits in user space. So your program calls create file function, but the create file function knows how to call the create file system file, it knows how to make the create file sys call that launches you into the kernel in the code in the kernel that creates a file. Very few people ever write system calls directly. Every once in a while, the only people who might do that are usually tend to be people who are writing device drivers, but even they don't use them all that often. It's very rare. Well, if you work for Microsoft and you're tasked with writing create file, then you have to write a system call. Okay, so if you wrote create file, if you were one of the Microsoft programmers and you wrote this function, you would have written a system call because this function has to make that system call. Now let's see, there ought to be here create okay. Now in your homework you called create process. Create process was a bare enough of a, it's a mess of a function. Guess what this create process system call is? It's even 10 times worse. The create process function, it gathers up all this data. There's these 10 function parameters, and each of these parameters points to data structures with dozens and dozens of more parameters. The create process function gathers all that data up and somehow passes it to the create process syscall. Okay, the create process syscall, create process functions in your code. The create process function gathers your data up in a bundle and somehow ships it to the create process system call, which is down in here, which is in the kernel. And it does it by creating this, by doing the syscall operation. See, okay, your code makes a function call to create process, then create process makes a system call to create process in the kernel, to NT create process. Okay. Oh, now NT create process, this system call, you can Google it. Various people will write documentation about it. I thought Microsoft had some documentation about it. Notice that Microsoft is kind of goes back. These system calls, like, notice that this is not a Microsoft website. Microsoft is very reluctant to document these system calls because they're part of the internal operating system. It isn't a security issue. It's a what they don't want is programmers using these numbers. Then when those numbers change, the program breaks and they blame Microsoft. And Microsoft says, but we told you don't use these numbers because we change them from time to time. But so they're reluctant to document this stuff because there are idiot programmers out there who think, oh, I'll speed up my code. I'll use this number directly. And then their program breaks a year or two later and they go, why did you break my program? And Microsoft says, you weren't supposed to use this internal documentation. You should be calling create process. They want you to call this function. They don't want you to call this system call because they change the system call from time to time. They're much more likely to update the system call than they are to update this function call. Okay, so this function call hasn't been changed in 30 years, but the system call probably has changed over time. They want you to call this function. They don't really want you to call the system calls directly. You call their functions and their functions call their system calls. But there are people out there who document the system calls. Okay, and I thought some of them are documented on Microsoft's website. Let's see if I'm not sure if I can remember where. There is some documentation of them on Microsoft's website. I just don't remember where I thought I would get it if I Googled NT create process. I thought I would get theirs. That's a company. They used to be. That's a company that wrote device drivers. I don't know if they went out of business. That was a company that had a huge amount of valuable information on their website because they were a company that wrote device drivers for other people, and they had a huge amount of documentation on their website. I wonder if they kind of died or something because, that's not there anymore. Okay. Okay. So the 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 system calls are not really well documented on purpose, but people have tried to document them. Like this guy's got this website where he gives you what's called the entry point, the vector. He gives you the entry point in the system call table for each specific system call. What's more interesting here is just the list of them. It's kind of interesting to see what the system calls look like. This is your interface to the operating system. You can create mutant, whatever that is. You can create a mutant. Okay. Some of these system calls do not have equivalents in this level because they're internal, they're system calls used by other system calls, or they're system calls used by the operating system themselves. So for example, I have no idea if NT create mutant is something that you could call if there's any what we call wrapper. This would be called a wrapper for the create file or create process. This is a wrapper for the create process system call. This is a wrapper for the create file system call. Okay, now there's something called create mutant. I have no idea if there's a create mutant system wrapper. Now this one there is. Create named pipe. That's an important function. Create named pipe is important. That's an important system call, and there is one for it. There is a wrapper for that one. Then there's here's all the create key, create timer, create file. So you can see where you can create different things. Like obviously create file is something that you would, there's a wrapper for it. There's a wrapper for create, there's a wrapper for create thread. Like there's not going to be a wrapper for this. Create a page file. We'll see what that is later on. That's not something that a user would do. So there's probably no wrapper for create paging file. Okay. All right. So now what's that? Remember, we were talking about states. So we're talking about a whole bunch of things at once. We're talking about this picture. Okay. Processes are running, ready. And there's this other thing here. Okay. So here's what's going on. What does this got to do with states? When this process wants to read data from the file, okay, so that's let's see if I can find it here. Here it is. Read file. Okay. There's the system call that would actually read data out of a file. Okay. And there's a wrapper for it. Okay. There's the wrapper function that your code can call. That's the wrapper around the NT read file system call. Okay. So that thing, read a file. We're gonna use it in class in a couple of days. We're gonna see how to play around with this function. So if I in this pick in here, what I would do is somewhere in my code there's a call to read file. Okay, so my code calls read file. But in the operating system is the NT read file syscall. And it's not really a function, so I'm not going to use function notation. So it's the read NT read file syscall. Okay, The NT read file syscall is sitting in the kernel. The read file function is been loaded into my, when you compile in your program, you compile into your code the read file function. Okay, so my program calls read file. Read file makes the system call into here, which puts, now that means I've switched from user mode to kernel mode, and I'm executing inside the kernel on behalf of this guy. Okay. And then the kernel says, okay, you want us to read something from the hard drive. Okay. So the kernel sends a message to the CPU to send a message to the hard drive to read some data. Okay. The trouble is that takes a real long time. Okay. So now we've come up to a really important idea. Some parts of the computer are way slower than other parts. The hard drive is really slow. To make this system call might take a few microseconds. To look up data on the hard drive takes milliseconds, but that's thousands of times longer than microseconds. Okay, the hard drive works on a scale of milliseconds, but the CPU acts on a scale of microseconds or even picoseconds, billionths of a second. In the time it takes the hard drive to look up a file, the CPU can execute thousands and thousands of instructions. So here's what the CPU doesn't want to do. It doesn't want to wait for the hard drive. Okay, when this system call is done to read data from the hard drive, the idea is that you should not just wait for the hard drive. The CPU should be busy doing something else while the hard drive is gathering the data up, getting it ready for you to copy it into memory. Okay, so we call this a slow system call. It's a system call that takes a long time to do. So what you do is you put this process that's this process is now, it called read file. Read file jumped into the syscall. The syscall sets up the operating system, tells the operating system to set up the access to the hard drive. And then this process is put in what we call the block state. And it stays in the block state until the IO operation is done on the hard drive. In the meantime, while this process is in the block state, the kernel does a context switch to another process and lets the CPU immediately get to work on another process. Now, what's happening is, in parallel, the CPU is running this process while the hard drive is doing the work that this process requested on that file. They're happening in parallel, simultaneously. And instead of the CPU on behalf of this process waiting for the hard drive to do its work, the CPU, the operating system is just more clever than that. The operating system says there's no reason why the CPU can't be working while the hard drive is working. So the read file syscall initiates an operation on the hard drive, which is going to take milliseconds and milliseconds and milliseconds. This process is put in the blocked state. So this process is put over here, blocked. And then the CPU picks another process to context switch to and runs it. Okay. So then when this running process makes the IO request, see, IO initialized, you get blocked. Now this guy's empty, so now somebody else is scheduled into the running stop. So the process that initiated the IO operations in here, and some other process got taken out of ready and put into here. Now, the CPU is running this other process. The hard drive is doing its work. At some point, the hard drive says, I've got all the data ready, and it generates an interrupt to signal it's done. That interrupt causes a trap of the CPU into the hard drive device driver. The hard drive device driver finds out from the hard drive that it's done reading the data. So the kernel, now you're in the kernel now. See, when the hard drive is done, sends the interrupt. The interrupt puts this thing into notice that this takes the CPU away from this process. you know, the CPU is running this process while this process is blocked, but this interrupt comes in. The CPU is diverted from this process by the interrupt into the kernel. The kernel communicates with the hard drive, says, oh, you're done with this guy's IO. So the kernel takes that process from blocked and makes it ready. See, IO done. Now, it just says, it puts that process in the ready queue saying, okay, we can now return from read file on this process, but we're not going to do it because this guy's still running. Okay, so this stuff here happens. This guy moves from blocked to ready while this one is actually running on the CPU. Okay, and you have to that's why I'm drawing these pictures. You have to like think through the steps of what's going on by staring at this picture. This guy initiated a file IO. So when he initiated the file IO, he's put in the block state while the hard drive does the work. This process is running in the meantime. So now this process is running and the CPU and the disk drive is running. When the disk drive is done with the IO operation, it signals the CPU, but that causes an interrupt. So that diverts the CPU temporarily from this process back into the kernel. The kernel says, okay, IO is completed for this process. So it takes that process and puts it in the ready queue. And then it returns from the interrupt and the CPU goes back to this guy until his timer interrupt happens. Then when his timer interrupt happens, you're back into the kernel, and the kernel sees that this guy is now ready because this guy is in the ready queue now. So now you can return to this process, which would return from read file. Okay. Actually, it would return from the it would return from the system call to read file, which in read file will return to my code. Okay. So when this thing gets running again, he'll actually complete the sys call to read file, and then read file will complete its call to where it was called in my code. This is an elaborate dance. You know, this is an elaborate system of hardware and software working together to create this, virtual CPU idea. Okay. Again, remember, the key idea is that you do not let this process touch that hard drive. The operating system must be the intermediary. Now, that's a security issue. Okay, so you don't let this process touch that hard drive for security reasons. But at the same time, if you did let him touch the hard drive, what would he do while the hard drive was doing the work for him? If he said, read a file for me, he's got to wait until the data is ready. The hard drive is slow. Now, he could write his code in what's called an asynchronous fashion, where he could read a file and then go do something else. But that's very few programmers program that way. You can write asynchronous function calls. That's a big part of things like JavaScript. But we're going to stick to non-asynchronous. We're going to stick to what are called synchronous function calls. So if he actually did call the hard drive, he would just be blocked doing nothing. And then the CPU would be doing nothing for a long time. So that's really inefficient. By making this thing direct through the kernel, by making the read file direct through the system call, you actually gain two benefits. One, you protect the hard drive. Only the trusted code in the kernel can touch the hard drive. Second, the operating system is designed so that when you're blocked waiting for the hard drive, the operating system says, okay, let's not waste CPU time. Let's direct the CPU into some other process. Okay. So the system call is actually solving two problems at once. It's solving a security problem and it's solving an efficiency problem. The security problem is preventing arbitrary processes from writing arbitrary data to the hard drive, because that's dangerous. And the efficiency issue is the operating system knows how to context switch between a process that's blocked and can't do anything and a process that's ready that's just itching to get the CPU back. So as soon as this guy blocks on waiting for the hard drive, the operating system schedules this other one. And in this picture over here, when the running process asks for an IO operation and gets blocked, the operating system goes here and picks somebody from here and puts them in the running queue and puts them in running, okay? So then it keeps the CPU busy. Now, what's not in this picture is the hard drive over here working. When it finishes the job of this blocked process, the hard drive informs the CPU through an interrupt, and then the operating system moves something from blocked to ready. Now, blocked you can have lots of processes blocked, okay? You could have 100 processes running, accessing 50 different files down here. And so you could have an elaborate mixture of processes that are blocked, waiting for file IO, processes that are ready, and one process that's running. Okay, one process running, probably a number of processes blocked, waiting for file IO. Like another example of waiting for, like if you ask for, we did this example a little while ago of this one. Remember, if you ask for something from the keyboard, you block until somebody types something in the keyboard and hits the enter key. So there's a real good example of blocking. When a Java function calls nextInt, it does not return until somebody types something at the keyboard and hits enter. In the meantime, the CPU's got nothing to do for this process. Until the CPU sees an interrupt from the keyboard that signals something's been typed at the keyboard, there's absolutely nothing for the CPU to be doing for this process. So this process, while it's waiting for a keystroke, this process will be in the block state, waiting for a keystroke. Then every time there's a keystroke, it gets put in the ready queue. Then it runs and captures that one keystroke. It's funny, the keyboard is actually kind of funny like this. Your program captures one keystroke at a time because it's blocked, waiting for somebody to tap a key. When a key is tapped, that means there's something ready. There's IO has been completed. There's a key ready. So the process that's blocked gets put in the ready state. When it gets its turn, it gets in the running state, and it grabs the one key off the keyboard. But then it wants another key off the keyboard, so then it blocks again, waiting for another keystroke. Okay. Now there's multiple ways of working with the keyboard. There's buffered and unbuffered keyboard. So what I just described is unbuffered keyboard. That would be this guy blocks for every keystroke. Buffered keyboard means this guy blocks until you hit the enter key. Then what it looks like is this guy's running and calls like read nextInt. Okay. What happens is it gets blocked. Then as someone's typing the keys, the actual system call is smart enough to say, I'm supposed to keep gathering keystrokes until I see an enter key. So then while the process is blocked, the keyboard device driver is gathering keystrokes up. When the keyboard device driver sees you hit the enter key, then it signals that the IO is done. Then your process gets put in the ready queue. Then when it goes back to running, it sees everything typed up till the enter. It sees the buffered keyboard. You can run your keyboard in two modes. You can run your keyboard where you block on every keystroke, or you block only up until you get an enter key. By default, Java and Windows do it the second way. By default, this thing blocks until somebody types the enter key. But you can also do IO in the what's called raw mode, sometimes referred to as raw mode, where you get every single keystroke. So you're running and you ask for one key, you block until one key is typed. Then as soon as the key is typed, you're ready again. Then when you run, you get that single keystroke. Then you block, waiting for another keystroke. Then when the second keystroke comes in, you're ready. Then when your turn gets to run, you run and you get one keystroke. Then you block on another keystroke. Games work this way because games need to react to every single keystroke. So games run in what's called raw mode so that every single keystroke is detected immediately. But Java system.in doesn't run in raw mode. System.in runs in what's called the buffered mode. So you don't see the int until you hit enter. So this thing stays in the block state. This thing stays in the block state until the enter key is typed. A game in raw mode would stay in the block state until just one keystroke is typed. Okay. All right. So now now notice that this stuff is spread over 2 chapters in the book. This is talking about the states, but this thing here, from here, this transition here from running to blocked is always done by a syscall. See, they could have put into this diagram a system call. Well, okay, not every system call makes you blocked. So there are some system calls that are like functions that the system call just immediately returns. There are some system calls that when this program makes the system call immediately has, it doesn't need to wait for an IO operations. So there are system calls where you transition to the kernel gets the information you need, and you answer right back. There is no blocking. So some system calls just keep you in the running state. You're running, but you transition from user mode to kernel mode back to user mode. Notice that in the running state, you can transition from user mode to kernel mode back to user mode. We'll look at some of these different system calls. We'll look at a system call that just goes into the kernel and comes right back, no block. But then there are other system calls that usually do IO operations. Those system calls, they take a long time to do. So you go in, the system call starts something up, but then the system call blocks you. Okay, so this would be a system call. That would be what blocks you, would be some system call. Not all system calls will block you, but the only way to get blocked is to make some system call. Okay, so I would have written system call here. But not every system call. An IO system, I guess to him, this is synonymous with the system call. It's an IO request. But system calls are in the next chapter. Notice that this stuff is very intertwined. It's hard to teach this stuff in a sense because it's not linear. There's a whole bunch of ideas that are just feed into each other. So this picture really needs the idea of system call. But system call is not until the next chapter. When you read this chapter, you kind of have to go back here and realize, oh, this is, that's telling me more information about this picture here. Okay. So you notice here, a process performs some kind of operation that makes it not ready. Well, what is that? That's a system call. See, he's being vague here. A process that performs some kind of operation that makes it not ready to run. Then in the next chapter, that some kind of operation is very specific. It's a system call. The process performed a system call that would take a long time to do. So that system call said to the operating system, system call jumps you into the operating system. The operating system said, this system call is going to take a long time. So I'm putting this process in the block state, and I'm going to let the CPU go do something else while something else does the system call. Maybe the hard drive, maybe the network interface card. So something else will do the system call work. And it's almost always a IO operation. The system calls that put you blocked, not always. We'll see. You can go from running to blocked. This is actually misleading. It does not have to be an IO operation. There are a number of other things that can put you from running to blocked that aren't IO operations. They are always system calls, but there are system calls besides IO operations that can put you blocked. Okay, and as we go on, we'll do examples of this. So I would the thing that really should be on that arrow is system call. A system call that takes, or what some people call, people refer to a slow system call. A slow system call, one that takes so long that your process should be blocked while the CPU goes and does something else. A fast system call is something where you just jump in, do the work, jump back out. You jump into kernel mode, do the work, jump back out. That's a fast system call. Those don't make you blocked. Okay. So sometimes people use the phrase slow system calls that would lead you to be blocked while the IO, while the whatever the slow system call is, while it gets handled. Okay. The easiest example of a slow system call is an IO operation, but it's not the only example of a slow system call. Okay. All right. See, here's where he talks about user mode and kernel mode again. Okay. He describes this pretty well. Yeah. You go, this stuff is not linear. Now it's written linearly. This is chapter 4, and this is chapter 6. And there's a short chapter in between if you want to read it. It's just like a 1 or 2 page. He tries to be humorous. So the chapter in between is kind of a little bit humorous. Okay. It's written as if it was linear, but this is not a novel. It's non-linear. You read this.
I love my voice.
Pardon me? Okay. Yeah, you read this, then you read this, then you read this again, then you read this again, then you read
You
this
guys
again,
are insane.
and you read this again, and you go back and forth. In fact, you probably read a page or two of this, and then you go back and see where there's a page or two of this that's referring to the page or two of this. They are intertwined concepts. You read them in a you have to. That's just the subject is unfortunately not straightforward enough. You can't linearize it. Okay, we have to on paper. So yeah, and remember, buried in the middle of all this is the memory management unit, which is another chapter later on. The memory management unit is part of this picture. And then later on, when we read about the memory management unit, you have to go back to these chapters and think about where in these chapters was the memory management unit actually involved. Because there's little things in this chapter that are really referring to the memory management unit. So the memory management unit chapter which would be chapter 13, it's intertwined with chapters 4 and 6. Okay, you kind of just, after you've really absorbed this, then you get to here and you're back to thinking, how does this interact with these? Because reading this chapter goes back and changes what your understanding of these chapters. There'll be things, there'll be details in these chapters that become clearer once you understand how the memory, this thing here sits between the CPU and the memory, and it's very much part of this picture. Okay, it's not. This is what makes operating systems a hard topic. It's not linear. Okay, different people, actually, different textbooks. Most textbooks order the topic the way this book does. Most textbooks on operating system do order it in the order of first do processes, then do virtual memory, then do files. See, files are over here. Processes, virtual memories, then files. In between, this is threads. So this is doing processes, virtual memory, threads, files. That's usually the order. You might, potentially you could do virtual memory before talking about processes, but it'd probably be even harder to order it in that way. So this seems to be the order that makes the most sense, but that's a false sense of linearity. There's a lot in here that needs this, that needs the virtual memory to understand. And there's actually stuff in, see this CPU scheduling? This is all a lie. The CPU scheduling is not scheduling processes. It's really scheduling threads. So everything in here, everything in this CPU scheduling chapter is really an approximation of the truth, because the scheduling is really scheduling threads. Okay, so everything in this chapter here is misleading. I often say in my classes, everything we tell you is a lie. Everything we tell you in computer science is a lie, because everything you're told is an approximation of the truth. Okay, because that's just easier way to explain things. Here's another way to think about that. This guy's a lie. There is no such thing as create process function. What do I mean by that? Why is he a lie? What's the real truth?
He's a function to the system call.
Yeah, the real truth is the create process system call. So this guy doesn't create processes. He's a convenient abstraction of the real thing. And in fact, then the thing that then the create then you think, oh, now I know the truth. Create file calls create process. Now, if you're a sophisticated computer scientist, somebody says, oh, I know the real truth. Create process function calls create process syscall, and it really does the system call. It really creates the process. Do you think that's true?
Given the way you're saying it, I'm inclined to say no.
No, of course it's not the truth. The create process system call is an abstraction of something else that's buried in the operating system that only Microsoft knows about. Okay? This system call is not the truth. This system call is itself another abstraction of something that's buried deep in the operating system that Microsoft has total control of. And then unless you get their source code, you don't really know what it does. Okay? So you've got layers of truth. The create process function, which is what most programmers care about. Most programmers don't care to know any more than what create process function does. A few people get curious and want to know what the create process system call does. And then if you work for Microsoft and you end up on the team that maintains the kernel, then you find out what create process system call really does. Okay. And at some point you find out what's really going on inside of the kernel. Everything you're told in computer science is a lie, because everything is an abstraction of something that's underneath it. Until you get to the final level of abstraction, the concrete implementation, but that can actually be that can often be buried away from you. It very well might be you have no access to what's the real truth. You know, it might be buried so deep in the operating system that you don't get to see it. So all of these functions are abstractions of system calls. And the system calls are themselves abstractions of something that's deep inside the operating system that we don't have access to. Okay, so there's not a linearity. Well, here there is a little bit of a linearity. Create file calls create file system call. So in this sense, that's a more direct level. There you have a higher level abstraction and a lower level abstraction. But quite often the abstractions are intertwined. You know, like process, virtual memory, and threads are just intertwined. Here they're taught as three abstractions, but in fact, they're just all one bundle of ideas. And it isn't until you've read all these chapters, when you've read all these chapters together, then you can start piecing it together. Then you can start getting a sense of what the real truth is. So we keep trying to attack it. We try to keep getting closer and closer to the truth, but it's tough. So my advice is, don't think you read this chapter and then you read this chapter and you've done with the reading. Go back and forth. You keep, and you might want to, like when you're back to this chapter and you're reading it, try to remember what you saw in this chapter and see if you can find where this chapter is making references to this chapter. Like a minute ago, some kind of operation. There's the little thingy that says, oh, some kind of operation is made clear in the next chapter. It's a system call, specifically a slow system call. Okay, all right. See, so that's important. I mean, it's real important to realize that really is slow system call, not necessarily an IO. It's not just an IO initialization. Okay, all right. Okay, we've run out of time. Let's see. We're going to look at on Wednesday. We'll look at some code that plays around with these ideas. Okay. Oh, I didn't even download the. We've been talking about the ideas, but this folder here, it's got code that lets us think about. There's some simple C programs. Okay. Oh, let me just show you one last thing. Let me tell you how everything's a lie, everything's an approximation, blah, blah, blah. See this picture here? That's just okay. here's what the picture looks like for Windows. There's the Windows state diagram. Okay, it's more complicated than the one in the book. See, the one in the book has 3 states. This one has 1, 2, 3, 4, 5, 6 states. And in fact, Microsoft keeps changing that picture. In another version of this book, it had a different picture. Look at that. Okay, this becomes this in the world of real Windows. 1, 2, 3, 4, 5, 6, 7 states with gazillion arrows between them. Notice how here there's only 4 arrows. You go from here to here to here and back and forth from here to here. Okay. So there's only 4 arrows here. Look how many arrows here. Well, this is the state diagram for Windows. Okay, and everything you learn is an approximation, and there's more layers of complexity under these approximations. But you start with these approximations, then you learn more and more details. Like there's a picture like this for the Linux kernel. It's probably simpler than the one for the Windows kernel. See, and also they're thread states, not really. See, there really aren't process states. They're really thread states. Okay, so we should quit there. We're out of time. All right, so we'll look at the code examples on Wednesday. We'll look at how we can turn this into actual code. Think about code. All right, so if you have questions about these things, send me email or come to office hours. And see, there's the homework assignment. Yeah, I have to give you. There's not a third programming assignment yet. I'm working on a third programming assignment. I hope to have it up there pretty soon. Okay. All right. So I'll stop sharing at this point. If you have questions, write me emails. Otherwise, meet on Wednesday. Whoops. What did I do here? I clicked on the wrong thing. You still hear me, right?
Yeah.
Yes.
Yeah, I don't know even what I clicked on. No, I'm lost. Okay, I see the end button. Okay, I'm going to click on the end button. Bye.